This is Professor Hildebrandt. I'm going to work another example for some calculations of how we measure our data from Chapter 3. On this example, it's a very basic example, but I'm going to cover how we would calculate variance and then standard deviation. And so if you remember from the text, these two measurements help us determine the spread of our data. So again, in my previous video, I went through mean, median, and mode and how those talk about the center of the data, the location, but variance and standard deviation are in the same family as range, which is showing the dispersion or the spread of our data set. So suppose this was, we're told this is the population. These are returns on stockholder equity. And so we have 4.3, 4.9, 7.2, 6.7, and 11.6. Very small population, but we're just going to assume that since we're told this is a population, these values represent all of the returns for a particular month. So first, let's review. Let's calculate the range. So recall from my previous video that to find the range, we simply take the highest and subtract the lowest. And so here, our highest value is 11.6, and our lowest value on those returns was 4.3. So 11.6 minus 4.3 means there's a range in our data from highest to lowest, a spread, we would say, of 7.3. However, this measurement is limiting because it only includes the highest and the lowest value. It doesn't include all the values that are in between, which is why we need the measurements such as variance and standard deviation. In order to calculate those, however, we have to get our arithmetic mean. And so recall again, a mean is just an average. So again, I'm going to go back to all of these and I'm going to just add up the values of all of these here. And then I'm going to divide by the total number, which is 5. So if we added these up, we would get 34.7. And then we're going to divide that by 5 to arrive at our mean. And so you can see here that our mean for this population is 6.94. So the average return is 6.94. That's how we would describe that in words. Okay, so moving on to the new stuff. Don't let this scare you too much, but this is our equation for calculating variance. We say that this is read as sigma squared. So that's the Greek letter sigma there, squared. And so sigma squared is equal to the sum of, that's what this one means here, the sum of all of our values in the population, that's our x, and then subtracting from that the arithmetic mean of the population. And then once we do that, we'll square it, and then we divide by the total number of observations in the population. I know looking at this equation might be a little bit frightening, but I promise you it's not too bad. I think the key to working out these problems and to do your calculations is to make yourself a table and just do one value at a time. Once you get all of the values squared, then sum those up and divide by n. So let me walk you through that now. Okay, so here we go. Again, it's not going to be too painful, hopefully. So I've listed out those returns on stockholder equity, 4.3, 4.9, 7.2, 7.6, and 11.6. Recall from the previous slide that our mean here is 6.94, so I'm going to write that up there so we remember. So all we're doing is taking the values in this first column and we're going to subtract that average of 6.94. And so we'll get negative 2.64. And then just because it's easier in your calculator once you have that value to continue on, in column 3, so this is what we do in column 2, in column 3 down here, we're going to take the value in column 2 and we're just going to square it. And so once we do that, we would get 6.9696 for the first value. Okay, 4.9 minus 6.94 is a negative 2.04. Again, we're going to square that for 4.1616. 7.2 minus 694 is 0.26. Hope you guys can see this okay. Once I square that, that is 0.0676. Then we do 6.7 minus the 6.94, negative 0.24. Again, square it for 0.0 576, and then lastly our largest return was 11.6, so we subtract out the 6.94 for 4.66, square that to get 21.7156. And so now what we're going to do is just tally up all those values in column 3, and we would get a total of 32.972. So what I'm saying here is the summation of all of our values minus the mean squared equal 32.972. And then remember, the next part of our equation was divide by n being the total number of observations in our population. And so in this very simple example, our population total is 5. So once we do this, we get our population variance, or our sigma squared, to be 6.5944. And so that is the final answer here for variance. Now, here's where variance is better than range. Again, range only includes your highest and lowest values in a data set. Variance is trying to tell us the spread of all, including all the values in our data set. So that is more helpful. However, because we have squared everything, whatever units we were originally talking about, in this case it's returns on stockholder equity, but it could be dollars, it could be miles, it could be a lot of different things. Your units now, once you have variance, is that original unit squared, which kind of loses its meaning. And so for that reason, the most common measurement used to describe the spread in data is actually standard deviation. Let's see if I can get that all to fit here. So we're going to take that variance and we're going to use standard deviation then to get back to our original unit. So standard deviation will just be, actually sorry, that's for the sample, will just be this sigma. It's going to be equal to the square root of, and then it's just our variance. But so when you see the equation in your book, it does look like this, which again is just that original equation that we were working with variance. So for this problem, plugging this in here, then our standard deviation is simply equal to the square root of the variance that we found to be 6.5944. So the square root of that, and if you plug that in your calculator, you would find it to be 2.568. And so that is the standard deviation in this very basic data set. 2.568 is the average distance that the returns are from that arithmetic mean. Now to take this just one step further, I'm not going to work this out, but I just want to point out that was for a population. What if we had a sample? So recall from earlier chapters that a sample is just a representative group from the population. So it's a smaller subset within the population to represent the whole. And so we use samples a lot when our data sets, our populations are very, very large. Okay. This is going to be almost the same. The equation for the variance is going to change slightly. So now it's s squared for the variance of a sample. It's still going to be the sum of all the observations. We're still subtracting the mean, but we call it x bar when it's the mean of the sample, and we're still going to square it. What's changing here is the denominator. It's going to be n minus 1. It's really technical, and so I'm really not going to get into that, but the basic gist of it is that if we just use n, it tends to underestimate the population variance, and so it's just something to remember. If you're asked to calculate the variation of a sample and not a population, your denominator needs to be n minus 1. And then again, going from the variance of the sample to the standard deviation of the sample, it would just be now s equals, again, the square root of this same equation that I just wrote up here. But let me write it for you one more time. So again, first calculate your variance. Once you have that, simply take the square root of it, and that gets you to your standard deviation for the sample. Hope this helps.